Cellulose acetate is one of the oldest and most commercially successful cellulose derivatives, bridging the gap between naturally occurring biopolymers and synthetic thermoplastics. Produced through the acetylation of cellulose, cellulose acetate combines the renewable origin of cellulose with enhanced processability, transparency, dimensional stability, and chemical resistance. Since its industrial introduction during the early 20th century, cellulose acetate has evolved from its initial use as aircraft dope and photographic film into a versatile engineering material employed in textiles, membrane filtration, packaging, medical devices, optics, and printing technologies. The growing emphasis on sustainable materials and the replacement of petroleum-derived plastics has further renewed interest in cellulose acetate because of its renewable feedstock, partial biodegradability, and relatively low environmental footprint compared with conventional plastics. Unlike native cellulose, whose extensive hydrogen bonding network makes it insoluble in most common solvents and difficult to thermally process, cellulose acetate exhibits excellent solubility in organic solvents and thermoplastic behavior. These characteristics permit manufacturing by solvent casting, extrusion, electrospinning, and fiber spinning, making cellulose acetate one of the most versatile bio-based polymers available today. Chemistry of cellulose acetate. Cellulose is a linear polysaccharide consisting of beta-1,4-linked D-glucose units. Each anhydroglucose repeat contains 3 hydroxyl groups located at the C2, C3, and C6 positions. These hydroxyl groups form extensive intra- and intermolecular hydrogen bonds, producing highly crystalline cellulose fibers with excellent mechanical strength but poor melt processability. Cellulose acetate is produced by replacing these hydroxyl groups with acetyl groups through esterification. The extent of substitution is described by the degree of substitution, which ranges from 0 to 3. The degree of substitution strongly influences the physical properties of cellulose acetate. As acetyl content increases, hydrogen bonding decreases, resulting in lower crystallinity, improved transparency, greater hydrophobicity, enhanced thermoplasticity, and increased solubility in organic solvents. Conversely, lower degree of substitution materials retain greater hydrophilicity and biodegradability. The acetyl content therefore determines not only the processing behavior, but also the final applications of cellulose acetate, from textile fibers to high-performance filtration membranes. Synthesis of cellulose acetate. Industrial cellulose acetate production begins with highly purified cellulose obtained from wood pulp or cotton linters. Lignin, hemicellulose, and mineral impurities are first removed to obtain nearly pure cellulose suitable for chemical modification. The conventional synthesis involves esterification using acetic anhydride in glacial acetic acid with sulfuric acid serving as the catalyst. Initially, cellulose undergoes complete acetylation to form cellulose triacetate. Controlled hydrolysis subsequently reduces the acetyl content to produce cellulose diacetate with the desired degree of substitution. The simplified reaction is cellulose plus acetic anhydride equals cellulose acetate plus acetic acid. Recent advances in green chemistry have introduced homogeneous acetylation methods employing DBU/CO2 switchable solvent systems. These catalyst-free processes minimize cellulose degradation, allow precise control over degree of substitution, facilitate solvent recycling, and significantly reduce hazardous waste generation. Types of cellulose acetates. Several commercial cellulose acetate esters are available, each possessing distinct chemical compositions and performance characteristics. Cellulose diacetate, CDA. Cellulose diacetate possesses a degree of substitution of approximately 2.2 to 2.5 and remains soluble in acetone. It exhibits excellent flexibility, transparency, and dyeability, making it the dominant material for acetate textile fibers, photographic films, cigarette filters, and packaging films. Cellulose triacetate, CTA. CTA approaches complete acetylation with degree of substitution values near 3.0. Compared with cellulose diacetate, CTA demonstrates higher crystallinity, superior heat resistance, greater dimensional stability, and excellent chemical resistance. Because of its exceptional salt rejection and chlorine tolerance, CTA became the benchmark material for early reverse osmosis membranes and remains widely used in forward osmosis and desalination systems. Cellulose acetate butyrate, CAB. TCAB is a mixed cellulose ester containing both acetyl and butyryl substituents. The bulky butyrate groups improve flexibility, impact resistance, weatherability, and moisture resistance while reducing brittleness. CAB is widely employed in automotive coatings, inks, lacquers, optical films, plastics, and specialty membranes. Cellulose acetate propionate, CAP. CAP contains both acetate and propionate ester groups. Compared with CAB, CAP offers higher toughness, superior optical clarity, lower moisture absorption, and excellent UV stability. These properties make CAP attractive for transparent packaging, optical applications, protective coatings, medical devices, and membrane technologies. Processing of cellulose acetate fibers and films. The thermoplastic nature of cellulose acetate enables multiple industrial processing techniques. Acetate textile fibers are predominantly manufactured by dry spinning. Cellulose acetate is dissolved in acetone to form a viscous spinning dope, extruded through spinnerets, and solidified as acetone evaporates. The resulting fibers are stretched to orient polymer chains, increasing strength and improving luster. Wet spinning and electrospinning are also employed for specialty fibers and nanofibrous membranes. Recent developments have explored melt spinning using external plasticizers such as triacetin to broaden the narrow processing window between melting and thermal degradation. Films and membranes are commonly fabricated through solvent casting or phase inversion. In solvent casting, cellulose acetate dissolved in acetone is spread onto flat substrates, followed by controlled solvent evaporation to produce transparent, uniform films. Membrane fabrication typically utilizes non-solvent-induced phase separation, NIPS, in which solvent exchange generates asymmetric porous structures suitable for filtration applications. Structure-property relationships. Cellulose acetate exhibits an attractive combination of optical, mechanical, and chemical properties. It possesses excellent transparency, high gloss, moderate tensile strength, low density, and outstanding dimensional stability. The polymer absorbs less moisture than regenerated cellulose fibers, while maintaining pleasant softness and silk-like aesthetics. Its reduced crystallinity improves processability compared with cellulose, enabling extrusion, thermoforming, solvent casting, electrospinning, and injection molding. Furthermore, cellulose acetate exhibits relatively good biodegradability because esterases first hydrolyze acetyl groups, allowing cellulase enzymes to subsequently degrade the regenerated cellulose backbone. Cellulose acetate membranes for filtration. Among all cellulose acetate applications, membrane filtration represents one of the most technologically significant. The breakthrough occurred in the early 1960s when Sidney Loeb and Srinivasa Soarirajan developed asymmetric cellulose acetate membranes for reverse osmosis. These membranes revolutionized seawater desalination by combining an ultra-thin selective skin with a porous support, dramatically increasing water permeability while maintaining excellent salt rejection. Reverse osmosis. Cellulose triacetate membranes dominated the reverse osmosis industry for nearly 2 decades owing to their excellent selectivity, chlorine resistance, and chemical stability. Unlike aromatic polyamide thin film composite, TFC, membranes, cellulose acetate tolerates continuous exposure to residual chlorine, reducing biological contamination and simplifying cleaning protocols. Although modern TFC membranes exhibit substantially higher water flux, cellulose triacetated membranes remain attractive for applications requiring superior chlorine tolerance and resistance to biofouling. Forward osmosis. Forward osmosis has renewed interest in cellulose triacetate membranes because of their smooth surface morphology and lower fouling tendency. Studies have demonstrated higher flux recovery after cleaning compared with polyamide membranes, making CTA advantageous in wastewater treatment and osmotic membrane bioreactors. Gas separation. Cellulose acetate membranes are extensively employed for CO2 removal from natural gas, hydrogen purification, and flue gas treatment. Their high CO2 solubility and favorable CO2/CH4 selectivity enable efficient natural gas sweetening. Nevertheless, prolonged exposure to high-pressure CO2 can induce polymer plasticization, increasing chain mobility and reducing separation selectivity. Strategies including cross-linking, polymer blending, and incorporation of nanofillers have been developed to mitigate this limitation. Emerging membrane technologies. Modern research focuses on mixed-matrix cellulose acetate membranes incorporating graphene oxide, carbon nanotubes, metal organic frameworks, MOFs, cellulose nanocrystals, silica nanoparticles, and zeolites. These nanocomposite membranes exhibit enhanced permeability, improved selectivity, superior mechanical properties, and greater anti-fouling performance, making them promising candidates for next-generation water purification and carbon capture technologies. Applications of cellulose acetate fibers. Cellulose acetate fibers possess a characteristic silk-like appearance, excellent drape, luxurious softness, and high luster. Consequently, they remain popular in fashion, textiles, linings, dresses, neckties, scarves, bridal fabrics, and decorative home furnishings. Their thermoplastic nature permits permanent pleating and wrinkle retention, unlike regenerated cellulose fibers. Medical textiles represent another growing application. Cellulose acetate fibers exhibit biocompatibility, softness, and sterilizability, making them suitable for surgical drapes, wound dressings, filtration media, and antimicrobial textiles after appropriate surface modification. Perhaps the largest commercial use remains cigarette filter tow, where cellulose acetate effectively captures particulate matter while maintaining low airflow resistance. Electrospun cellulose acetate nanofibers have also attracted considerable interest for tissue engineering scaffolds, drug delivery systems, air filtration, protective clothing, and smart textiles. Applications of cellulose acetate films. Cellulose acetate films combine optical clarity, flexibility, heat sealability, printability, and dimensional stability, making them indispensable in numerous industries. In packaging, cellulose acetate films are employed for food wrapping, blister packaging, labels, window films, and biodegradable packaging materials. Their transparency and oxygen barrier properties improve product visibility while extending shelf life. Within the graphics and printing industries, cellulose acetate films serve as printing substrates, overhead transparencies, overlays, photographic films, graphic arts media, playing cards, security printing, and protective laminates due to their excellent printability and dimensional accuracy. Optical-grade cellulose acetate films are used as polarizer protection layers in liquid crystal displays, touch panels, and photographic imaging. Their low birefringence, high transparency, and UV stability make them valuable in modern electronic displays. Additional applications include pressure-sensitive adhesive tapes, release liners, decorative laminates, pharmaceutical coatings, biodegradable composites, and protective coatings. Challenges and future perspectives. Despite its numerous advantages, cellulose acetate faces several limitations. Its relatively narrow thermal processing window necessitates plasticizers such as triacetin to improve melt processability. Long-term plasticizer migration can compromise mechanical properties and dimensional stability. Furthermore, solvent-based processing remains energy-intensive and requires efficient solvent recovery systems. Future research is increasingly directed toward bio-based plasticizers, greener acetylation chemistry, recyclable solvent systems, nanocomposite membranes, additive manufacturing, and multifunctional cellulose acetate materials capable of sensing, antimicrobial activity, and controlled drug release. Advances in circular manufacturing and renewable feedstocks are expected to further expand the role of cellulose acetate as a sustainable engineering polymer. In conclusion, cellulose acetate remains one of the most versatile and commercially important cellulose derivatives, combining renewable origins with excellent optical, mechanical, and processing characteristics. Through controlled acetylation, a family of materials, including cellulose diacetate, cellulose triacetate, cellulose acetate butyrate, and cellulose acetate propionate, has been developed to satisfy diverse industrial requirements. Among these, cellulose acetate membranes have played a transformative role in reverse osmosis, forward osmosis, gas separation, and water purification due to their excellent chlorine tolerance, fouling resistance, and tunable selectivity. Beyond membrane technology, cellulose acetate fibers and films continue to find widespread applications in textiles, medical products, packaging, graphics, electronics, and optical materials. Continued innovation in green synthesis, nanocomposite design, and sustainable manufacturing is expected to ensure that cellulose acetate remains a cornerstone bio-based polymer for advanced materials engineering in the coming decades.